Hello there and welcome to the course Probability Methods in Civil Engineering. In today's class, we are going through this module 2 which is random events, and today is the third lecture in which we will cover the part called Axioms of Probability. So, these axioms are basically the fundamentals to the probability theory, and any conclusion that we generally draw in the theory of probability, these are generally directly or indirectly somehow it is based on these axioms of probability. So, to know the theory of probability, understanding these axioms are very important. So, why it is important that we should know first the probability of an event A. In the previous classes we have covered this concept of event and sample space. So, here when we are going to assign probability to some event, we generally follow certain norms. So, here probability of an event A, which is denoted as PA, is assigned in such a way that it satisfies certain conditions. These conditions are known as axioms of probability. There are three such axioms that we will go one after another. In the development of this probability, as we just discussed, is that in the development of this probability theory, all conclusions are directly or indirectly based on these axioms. So, the first axiom says that for any event A which belongs to the sample space S as shown in this figure, which is should lie between the numbers real numbers 0 to 1. So, it should be greater than equal to 0 and it should be less than equal to 1. So, this axiom states that the probability are real numbers on the interval from 0 to 1. Obviously, here one point should automatically be known, that if a particular event that have no point, if the event is a null set, then obviously the probability of that event equals to 1. On the other hand, if the event consists of the full set, which is nothing but the axiom 2, and here we go for this axiom 2, is that the probability of the full sample space or the certain event which is denoted as S, the sample space, the probability of S equals to 1. So, if the event consists of all the sample space, that means any one of this event is a certain event. So, that is why the total probability, which is probability of the full sample space, which is equals to 1. This axiom states that the sample space as a whole is assigned, sorry for this spelling mistake, this will be axiom. This axiom states that sample space as a whole is assigned to a probability 1, since S contains all the possible outcomes, the S is a certain event. So, this is the second axiom of the probabilities. The third axiom states that for any two mutually exclusive event, now in the last class we discussed about this mutually exclusive event. The two mutually exclusive events means the two event, if there is nothing in common. So, then the occurrence of one event automatically implies that non-occurrence of the other event, then these two events are known as mutually exclusive event. So, this axiom 3 states that for any two mutually exclusive events A and B, that is A intersection B is a null set, then probability of A union B is the summation of their individual probabilities, that is probability of A plus probability of B. So, this axiom states that the probability of the union of two events is the summation of the probability of the individual event if the events have no outcome in common. So, if the events have no outcome in common, that means that there is no space, there is no overlap between these two events, as it is shown in through this Venn diagram, that is the intersection between two events is a null set. Now, based on these three axioms, there are few elementary properties are there. Those are very useful to draw a certain conclusion from the from these axioms. That we will go one after another. The first elementary property that we can draw from this one is just the extension of the last axiom that we have seen. If A1, A2, and in this way these are mutually exclusive events, then following the third axioms, that is probability of the union of these events is simply the summation of the probability of all such events. So, this is basically an extension of the third axiom to include any number of mutually exclusive events. This is known as the property of infinite additivity. So, for a sample space, if we see, if we can have the different events, then, and if we say that these events are not overlapping to each other, then if we want to know what is the total probability of occurring any of these events, then that can be achieved, that can be obtained by simply summing up the probabilities of the individual events of summation of those probabilities for the individual events. Second elementary property says, if A1 is one event which is belongs to A2, that means if you refer to this particular Venn diagram, you see that this A1 is a subset of this bigger set A2, which is denoted here as that A1 belongs to A2, then the probability A1 is less than equals to probability A2, and probability of A2 minus A1, which equals to probability of A2, probability of A2 minus probability of A1. So, in this Venn diagram, to represent this one, this probability of A2 minus A1 is nothing but this dark red area, which is nothing but this probability of A2 is the total probability as shown in this inside the bigger circle, minus the probability of this small subset of this A2, which is quite straightforward from this Venn diagram representation. The third property is, if that A complement, that is A bar is the complement of the event A, then the probability of A complement is equals to 1 minus probability of A. Here one thing is that that event A and its complement union of these two events consist of the full set. Now, if you see here, if this is your if this is your full sample space, then, and if this is your event A, then the event A and the event, this area is your event A complement. That means the union of these two event is nothing but the full set, which is your full sample space S. Now, from the second axiom, we know that probability of S is equals to 1. So, what we can, so this S we can break by probability of A plus probability of A complement, so that we will get this R equals to 1. So, this probability of A complement is equals to 1 minus probability of A. So, from this second axiom we got this particular conclusion, which is shown here, that probability of A complement is equals to the total probability, which is 1 minus probability of A. Then the next property says that if we say it is just in the sense, it is just opposite to the last property. Here if we say that one event which is the union of different n numbers of mutually exclusive events, as it is written here, if A is the union of A1 to AN, where A1, A2, AN are the mutually exclusive event, then the probability of the total event, that is A, is nothing but the summation of probability of A1, A2 up to probability of AN, which is again the extension of those that we just discussed, that third axiom. That in the third axiom we have seen that probability of A union B is equals to your probability of A plus probability of B. That means now if I say that probability of A plus probability of B, now in other side we are just saying that A is the split up of, say for example, A1 and A2 which are mutually exclusive, of course, then probability of A1 union A2 is equals to probability of A1 plus probability of A2, and this A1 union A2 is nothing but probability of A, which is equals to probability of A1 plus probability of A2. Now just by going on this induction, if I just say that this A is the union of, so I can write that A equals to the union of these events up to AN, then obviously the probability of A should be equals to probability of A1 plus probability of A2, and in this way it will go up to probability of AN which is here shown in this diagram, that if these are the partition in such a way that these are mutually exclusive events, then the probability of A should be equals to the summation of their individual probability. So now if I replace this A, so this is also going to this, if I just replace this A in terms of this full set, full sample space, and this full sample space is partitioned like this, and it is collectively, if it is exhaustive, then we can say that probability of A1 plus probability of A2 up to probability of A1 is equals to probability of S, which is nothing but equals to 1. So if the full sample space is partitioned into A1, A2 up to AN, which are mutually exclusive and collectively exhaustive, then the summation of these probabilities are equals to 1. So this one also we discussed in the last lecture also. For any two events in the sample space, this is the fifth property now. For any two events A and B inside this sample space, which is shown in this Venn diagram, one is that black shaded circle and one is a red circle. These are two events. Now any one event, the probability of the one event can be expressed in terms of this expression. Now if we just see here, that is, this is your full sample space. Now we are having the two events A and B. Now if we want to know what is the probability of A, this is equals to, what we are doing is that this probability of A, we are just making it the summation of two zones. One is that this red shaded zone, and another one is this particular black shaded zone. Now what is this, that your red shaded zone? This red shaded zone is the probability of A intersection probability of B. So this much is done. Now what is this black shaded zone? This black shaded zone again is the intersection of two events. One is that B complement. So outside this B area, the full area is the B complement intersection with A. So which is nothing but this black shaded area. So which is your B complement intersection A. So these are the two events. So this event corresponds to this red zone, and this probability corresponds to this zone. So this two summation is nothing but your probability of A. Here if you see that this probability, if you see the monitor here, you see that this probability of A is equals to probability of A intersection B, which is nothing but this zone, and this A intersection B complementary, which is nothing but this area. So one particular, the probability of any one event can be expressed in terms of the summation of its partition, which is in terms of this two events in the sample space. The next property tells us that if A1 and A2 are any two events, then the probability of A1 union A2 is equals to probability of A1 plus probability of A2 minus probability of A1 intersection A2. This is important in the sense, you see, as if you compare this property with respect to the third axiom of this probability, then you see that here it is the any two events. We are not putting the constraint of this mutually exclusive event here. So here this A1 and A2 need not be mutually exclusive. So if these are any two events, then this is the expression that that holds. If you now see here that if in this area there are two events, again what we are trying to get is that is the union of this is your A, and if this is your B, then what we are trying to get is the probability of A union probability of B. So what is this probability of A union B? Is this green area. If I just draw it in the along the side of this circles, this union concept was given in the last class. So this is your union of two events. Now these two events, so how can I express this one? First thing, from this thing I can write probability of A. That means I am just writing it, I am just shading it, the area, corresponding area here in this Venn diagram, which is this is your probability of A. Now I am adding it up, probability of B, which is again I am just shading it in this is the area. So if you see, while adding up these two probabilities, we are adding this area twice, one which is there in probability of A and also in probability of B. That's why this area has to be deducted. So this is minus probability of A intersection probability of B. So this is the graphical representation of this particular equation. Now this equation can also be proven in terms of this what we have seen, the representation of one event in terms of the event in some two different event in the sample space. So if we see that proof, it states like this, that probability of A union B can be expressed in this way, that probability of A intersection B plus these two. Now again, if you refer to this diagram, that this probability of, I will just take a separate sheet again. So now this one, this is A and this is your B. So probability of A union probability of B, which is equals to, I am just separating it out into three different places. One is, the first one is this place, second one is your this area, and third one is your this particular thing. So then what we are getting is this, the middle one, that is the intersection part, probability of A intersection B, plus, so this first area, the way that we can write is that this is nothing but the intersection between the B complement, that is outside B, and intersection with the event A. So this will give you this red shaded area, so which I can write as this probability of A intersection B complementary. So this one corresponds to this red shaded area. Plus, similarly, if I want to write this black shaded area, which is probability of A complementary intersection B. Now these events can be written that probability of A intersection B plus probability of A intersection B prime. I am just clubbing these two parts together, plus I am adding one more part, which is probability of A intersection B, plus I am taking this term, which is probability of A complementary B intersection with B. So I have added one part here, so I have to delete this part to make this equality, probability of A intersection B. Now this one, if you just match, and this one if you just match with our fifth property that we have seen in the monitor, if you see, if you just see in this one, then in the fifth property, then what we can do here, if you see it here, so this we can write as probability of A, and similarly this we can write as probability of B, and obviously this minus probability of A intersection B, which is obviously this A union B. So this proof is given here on this slides also. So these are the breakup of three probabilities, which is shown in the Venn diagram there, and there are some algebraic calculation to get this proof. The next property, rather I should say that this is the extension of, instead of having these two events, if we have more than two events, if we have the three events, then this will be simply the extension of this thing, which can be easily shown in terms of this Venn diagram. Here what we are saying that if this A1, A2 and A3 are any three events in the sample space, then what is the probability of A1 union A2 union A3. So similarly, what we should do, we should add up this probability of A1, which corresponds to this circle here, you can see, probability of A2 this one, and probability of A3, which is this. Now after adding all these probabilities, what we are doing, that we are adding individual intersection, the pairwise intersection of these probabilities twice. So we have to deduct that part. So we are deducting this first pair A1 A2 minus A2 A3 minus A3 A1. Now while doing this deduction from this one, we can see that this particular area has been deducted once more. So we have to add this particular area, which is the intersection of all three events. So we have to add this part, that is probability of A1, A2, A3 intersection. So this is just a simple extension of this earlier thing. If you just see, if you just take out this part and this part, you will see that this part has been, whatever the extra, that part has been deducted. Again, when you are taking the third pair, this is one negative area is coming here, so that you have to add here to get these two are equal. So this is the extension of this last property, which is discussed in terms of two events. Here it is in terms of any three events. Now, it is just a opposite sense of what we discuss in this fifth property. This says that if an event A must result in the occurrence of one of the mutually exclusive event in A1, A2 and up to AN, then the probability of A can be expressed their individual intersection. If you just see it here, that so if there is, this is your sample space, and this sample space is having the partition like that, mutually exclusive and collectively exhaustive partitions are there, and there is another event like this, and if I say that these are all these partitions where this is total S, this is partition is A1, A2 and up to this it is going and it is coming up to AN, and if I say that this event is your A, then this probability of A can be expressed as a summation of this particular area. First is this area. So, what is this area? This area is nothing but the intersection between the event A and event A1. So, we just write it, event A intersection event A1 plus I am writing now this area, this corresponding area in this Venn diagram, which is nothing but probability of intersection of A2 and this event A. So, A intersection A2. In this way I will go on adding up, then this area will come, then this area will come, then this area will come, and finally the last event will come. So, in this way I will just add up to probability of A intersection AN. So, this is stated here in this slide, that if an event A must result in the occurrence of one of the mutually exclusive events A1, A2 up to AN, then probability of A is the summation of the intersection of that event with the individual events A1 up to AN. So, the next property, before we go to that one, that is on the conditional probability, that we will see in a minute. Before that, we will just see, we will just quickly go through one small example problem which states like this, that if a steel section manufacturer produce a particular section and the initial quality check reveals that the probability of producing a defective unit is 0.022, further investigation reveals that the probability of producing a defective unit in terms of the measurement is 0.01 and the defective unit in terms of the material quality is 0.017, then what is the probability of producing an unit that is defective in measurement as well as in material quality. So, here what the information is given is that what is the total probability of producing a defective unit is given, and these two events, that is probability of it is defective, it can be defective in two different ways. One way of defective unit is that its measurement is the measurement was wrong, and other one is that the material quality was not satisfied. So, in two different ways the particular section can be defective. So, their individual probability that we got is 0.01 and another one is 0.017, and the total is given here, this 0.22. And the question is what is the probability of producing an unit which is defective in terms of both, that is it is defective in terms of the measurement and also in the material quality. So, we can assign two different events. The first event is that it says that it is event A. That event says that the event of production of a defective unit in terms of the measurement. So, this is your first thing, and the second is that B, that is event of production of the defective unit in terms of the material quality. So, from the problem the information that is supplied is the what is probability of A and what is probability of B. So, probability of A is your 0.01 and probability B is your 0.017, and it is also supplied that what is the probability A union B, that is the whatever way it is, the defective unit probability of defective unit is 0.022. So, here the idea is that this, when we are saying that probability of A union B, that means if we again refer to that Venn diagram, that A and this B. So, this A union B, that is when I am saying that the unit, a particular section is defective, it can be anywhere. It can be either, it can be defective in case of only for the reason, only for the event A, it can be defective by both, or it can be defective by the second reason, that is event B. So, that is why whatever the probability of a defective A unit, that is the value is given 0.022, this should refer to this probability of A union B. So, thus this probability of A union B is given 0.22. Also, we have seen that probability of individual event, that is probability of A, is given as 0.01 and probability of B is given as 0.017. So, now it is asked that what is the probability that a particular unit is defective in terms of both, that is in terms of its measurement as well as the material quality. Now, so here according to this Venn diagram, we are basically referring to this intersection of these two event, that is we want to know what is the probability A intersection B. Now, we know to do this one, that's one simple property that we have used. We should use this one, that is probability of A union B is equals to probability of A plus probability of B minus probability of A intersection B. Now, this is known to, this is known and this is known, obviously this should be known, which is probability of A intersection B equals to probability of A plus probability of B minus probability of A union B, which is 0.01, 0.017 minus 0.022 equals to 0.005. So, this refers to this particular area where I can say that this unit is defective in terms of both measurement as well as your material quality. This is a simple application of that that property that we discussed, that if there are two events which are any two events, it does not mean that these two are mutually exclusive, then we can use this property to get that simple answer. The next thing which we are going to cover is known as the conditional probability. Here this conditional probability means in the sample space, what happens, these two events are given and we are interested to know the probability of a particular event given some condition that other events has already occurred. Now, if these two events are shown here, as you can see in this Venn diagram, that is this is the area that corresponds to this event A, and this red is the corresponds to this B, and this overlap between A and B is nothing but the intersection of these two. So, now if we want to know what is the probability of B, this can be obtained from this the technique that we discussed in the previous class. Obviously, we can also know what is the probability of of the individual events, probability of A as well as probability of B. Now, here the question that we are putting is the conditional. It is conditional means that I want to know the probability of one event, any one of these two events, that probability of A or probability of B with certain condition. Here the condition is that I am ensuring that occurrence of the other event. The occurrence of the other event here means that here it means that if that A and B are two events, are means to be specific any two events in the sample space S, and the probability of A is not equal to 0, then the probability of B given that A has already occurred. Now, the probability of B means there is no condition is given here, which we simply write in terms of the probability of B. Now, what we are seeing is that this is your probability of B. Now, when we are saying that that probability of B, but given A has already occurred. So, this we generally denote as probability of B given A. So, this is the notation for this one. So, the probability of B given that A has occurred, and this is just simply the probability of B. Now, if we come back to this one, then we see that which is denoted as probability of B given A, and this is expressed as probability of B given A is equals to, this should be equals to, not 3 1, sorry for this mistake. So, this is equals to probability of A intersection B divided by probability of A. Now, if we just refer to this Venn diagram that is shown here, is that this is your probability A and this is your probability B. Now, from the traditional definition of this probability, we will just see. So, we are interested to know the probability of B on condition A. Now, there must be something in the numerator and something in the denominator. So, in this denominator, what we should get, it is the total possible space that we know from this. In the previous classes, we discussed that this denominator should be the total possible case. Now, here what is the possible case? The possible case is that that given A has already occurred. So, now if A has already occurred, so I should ensure that the whatever the outcome of the experiment, that outcome of this experiment is certainly within this region, should corresponds to this particular area of this Venn diagram. So, this is already in this one. When we are talking about this probability of B, the total feasible or total feasible space or the total sample space is your full sample space. Now, when we are giving some condition, the condition that A has already occurred, so my feasible space is this total, this A. So, obviously, in the denominator this probability of A should occur. Now, in the numerator we know that we should put the quantity which is the favorable case. Now, we want to know what is the probability of B, condition that A has already occurred. A has already occurred, that is why we put in the denominator probability of A. Now, what is the probability of B? Now, the success area being within this area, the success area is nothing but this area. If it is in this area, then we can say that B has also occurred. So, what is this area corresponds to? This area is nothing but probability of A intersection B. So, this is the expression for this conditional probability, which says that probability of B given A has already occurred, which is equals to probability of A intersection B divided by probability of A. So here, so the same thing has been shown here, which is the probability of A intersection B is this shaded area, which is orange type area, and probability of A means this green area plus this orange this area, this intersection area. So this is the conditional probability. Now we will see the application of this simple simple conditional probability equation to some civil engineering related problem. Here on a national highway, a stretch of 10 km is declared to be the accident prone zone. Now over this stretch, the probability of accident at any place, sorry for the spelling mistake, at any place is equally likely. Now here, when you just recall some of our previous class, here the equally likely means that I am just giving an attribute how to assign the probability for a particular event. So here the event means that one accident is taking place at any over any particular substretch of this 10 km area, and it is equally likely. So in the middle of this stretch, this 10 km stretch, there is a bridge of 755 meter length. Now given an accident has occurred within the first 6 km stretch, what is the probability that it has occurred on the bridge? Now this is interesting in the sense that, so my total stretch is this, starting from 0 to 10 km. Now I say that this is equally likely accident prone area and it is equally likely. So if given that any stretch, if I just give from 0 to or from the any kilometer edge from h1 to say h2, the probability of the accident between these two range, the probability of, if this is some event say E, then probability of E should be equals to h2 minus h1 divided by 10. So this we can get from for the any event that we can assign, as these are equally likely. Now for this problem, if we just assign that this is say A is one event, that event of accident within the first 6 km. So what is the probability of A that we will get here is nothing but, so 6 minus 0 divided by 10 minus 0, which is 0.6. So from starting from here up to 6 km range, the probability of accident in between these two is your 0.6. Now if I assign if I just denote another event, the event of accident on the bridge, here the bridge is 755 meter length. So the probability of B will be, it is equally likely all over the stretch. So this is also equally likely. So this is 0.755. I am just converting it into kilometer, which is 0.0755. So our condition, so here the what is the probability that we want to know is that the probability of B, that is it should occur on the bridge. What is the probability that it has occurred on the bridge, that is the event B, on condition that it is occurred within the first 6 km of the stretch. So this is B given A. Just by putting it here, the probability of then A intersection B divided by probability of A. Now this probability of A intersection B can be, so you have to see at the middle of this bridge. So, if this is the location of this bridge, then this is your 5 kilometer. So, a bridge has some length and this is within this first 6 kilometer most probably comes here. So, this is your 755 meters. So, the full bridge is coming within this first 6 kilometer range. So, that means that A intersection B is nothing but, so B is a subset of A. So, the intersection obviously will be within this region. So, which is nothing but equal to the probability of B. So, which is the probability of B that we got earlier is that 0.0755 divided by probability of A is 0.6, which is 0.126 as we got in this calculation. So, here if you just compare that, what is the probability of B is your 0.0755. So, this is the probability that we got. Now, when we are giving some condition, that probability information changes. This is the useful thing that we should know, that if we give some condition, then the probability of the same event may change, as we have seen in this particular problem as well. So, here you can see that this probability of B given that A, it comes to be 0.126. So, in this class we have seen that there are 3 axioms that defines the basic properties of the probability of events in a sample space, and the probability theorems formulates the probabilities of an event when other event exist in the same space derives from these axioms. The special probability theorem based on this theorem explained here will be discussed in the next lecture. But before I conclude, I just want to add one point here. When we are talking about these axioms of this probability, one thing should be kept in mind, that this axioms of probability never tells how should we assign the probabilities. It only gives some guidelines that how the probability should be assigned, but what should be the actual probability of a particular event, it is nothing to do with the axioms of probability. So, if we just see that the last example that what we have done is that it is that when we are talking about this probability of B and probability of A, or whatever we have just seen, that these are coming from the equally likely probable events, all these things that we discussed in the last class. Only thing, the axioms tells that there are some certain guidelines that must be followed to get to assign these probabilities, but what should be the actual probability for a particular event is nothing to do with the axioms of probability. So, with this I conclude this class. In the next class, some more properties and the special probability theorem will be discussed in the next lecture. Thank you.